Hi, I'm Alan. I'm from MIT, and today I'll be talking about better algorithms for estimating non-parametric models in crowdsourcing and rank aggregation. And this is joint work with Ankur and Moitra. So first, let us begin with the problem setup. The problem is about estimating shape-constrained matrices from noisy observations. More specifically, we'll consider the following classes of matrices. First, define the class of bivariate isotonic matrices as the matrices whose rows and columns are sorted in increasing order and whose entries are in 0, 1. For a matrix M in permutations pi and sigma, let M pi sigma be the matrix obtained by permuting the rows and columns of M according to pi and sigma respectively. So we'll be considering bivariate isotonic matrices with permutations acting on their rows and columns. Now, as a quick example, we have on the left a bivariate isotonic matrix, and the matrix on the right is obtained by reversing the rows and the columns. Now, the specific question that we seek to answer is the following. We observe M pi sigma plus E, where M is bivariate isotonic, pi and sigma are unknown permutations, and E is a noise matrix. For simplicity, let's think of E as having entries drawn from a normal distribution with mean 0 and variance 1. There are some technicalities that we deal with in the full paper, but we will not worry about them here. Now, given these noisy observations, our goal is to recover the underlying matrix M. So it's worth noting here that the size of the noise matrix E is comparable to the size of M. And that means that individually, each entry that we observe contains essentially no signal. The problem that we just posed has several applications. For instance, in crowdsourcing, we can consider a set of workers and a set of tasks. So the rows of the matrix are represented by workers, and the columns correspond to tasks. And then the entries of the matrix are the probability that a worker successfully completes a certain task. And note that some tasks are inherently more difficult than others, and some workers are inherently more skilled than others. And that's where sort of the permutations come in. Now, also in noisy sorting and rank aggregation, we can imagine that we want to rank n elements, say x1 through xn. And so we have a matrix Mij, where the entries are the probability that xi beats xj in a pairwise comparison. So this corresponds to a slightly special case of the bivariate isotonic model, where we also assume that Mij plus Mji is equal to 1 for all ij. And also the permutations pi and sigma are the same. And this slightly specialized model is commonly called SST, or strongly stochastically transitive. Now, the permutation-based models that we're considering here have several advantages. The most important one is that these models are non-parametric. And instead, the only assumption we're making is that there's some sort of transitivity. This means that these permutation-based models are more flexible than many commonly used models. For instance, the Dewey-Skeen model in crowdsourcing assumes that essentially when we have the matrix of workers and tasks, that matrix is rank 1, which is much more restrictive. And in noisy sorting, there is a commonly studied model, say in Braverman and Wassel, where they assume that each comparison gives the correct answer with 2/3 probability and the incorrect answer with 1/3 probability. So compared to these more restrictive and parametric models, the permutation-based models are validated by empirical studies, whereas many of the more restrictive models are actually invalidated by empirical studies. So in a seminal paper by Ballinger and Wilcox, they state, all of these parametric CDFs are soundly rejected by our data. However, SST usually survives scrutiny. Now I'll briefly survey some previous work on permutation-based models. In a paper by Shah et al. In 2016, they introduced the problem of learning from permutation-based models. They give a spectral estimator that achieves an error rate of n to the negative 1/2, and they prove that the information theoretically optimal error rate is n to the negative 1. By error rate here, I mean normalized Frobenius squared error. So the Frobenius squared error between your estimate and the true matrix, and then divided by n squared. To attain the information theoretically optimal error rate, their algorithm requires brute force searching over all possible permutations, which is computationally infeasible. So their work naturally raises the question of whether there is a computational versus statistical gap for learning permutation-based models. In a paper by Mao et al. In 2018, they narrow the computational statistical gap by giving an estimator that achieves an n to the negative 3/4 error rate and is computable in n to the 2.5 time. In our work, we improve upon the previous results in terms of both computational efficiency and error rate. So first, in the specific case where there is only one hidden permutation. So say the columns are perfectly sorted and the rows are permuted according to pi. We develop an estimator that is computable in nearly linear time and achieves an error rate of n to the negative 1. So this matches the information theoretic threshold. And it's worth noting that the previous work by Mao et al., they are still stuck at n to the negative 3/4 even in this special one permutation case. Next, in the two permutation case, we develop an estimator computable in nearly linear time that achieves an improved n to the negative 5/6 error rate. And to do this, we introduce several new ideas to break the barriers at n to the negative 3/4. Now let's go into some of the technical tools that we introduce. First, for these permutation-based models, it's important to note that estimation reduces to sorting. More specifically, it suffices to estimate the hidden permutations, so to compute estimates pi prime and sigma prime. And this is due to a theorem by Mao et al. In their paper where they state that once you have estimates pi prime and sigma prime, it suffices to run isotonic regression with those estimates. And then if your permutation estimates are good, your overall estimate for the matrix will be good. Now let's better understand the barrier at n to the negative 3/4. So the first thing is that n to the negative 3/4 is a barrier to all pairwise comparison algorithms. So any algorithm that sorts the rows and columns only by comparing them two at a time cannot be n to the negative 3/4. And this lower bound holds even when we assume, say, that the columns are already sorted. This is, again, a theorem from the Mao et al. Paper in 2018, where they prove that there exists. So essentially what the theorem says is that there exists two rows R and R prime, such that their Frobenius squared error is n to the 1/4, and yet information theoretically they cannot be distinguished. So what this means is if you have a matrix with n over 2 copies of R and n over 2 copies of R prime, then any pairwise comparison algorithm cannot distinguish any of the pairs of R and R prime. So then this row-wise error of n to the 1/4 leads to a normalized Frobenius squared error of n to the negative 3/4. There are a few further limitations to existing algorithms that make them get stuck at n to the negative 3/4. So first is that the existing algorithms compare rows and columns through partial sums. So for instance, the algorithm in Mao et al. Compares two rows by looking at their sums over some contiguous interval. And they even conjecture in the same paper that all such algorithms cannot beat n to the negative 3/4. Also, existing algorithms are one shot, meaning that they estimate the row and column permutations in one shot. And instead, they do not, say, estimate the row permutation and then use that to estimate the column permutation at a finer scale, and then make progress iteratively, so on and so forth. So we introduced several new ideas to overcome these barriers. First, instead of considering just sums of contiguous intervals, we compare rows using their sum over a union of contiguous intervals. And then to overcome the pairwise comparison barrier, we use information from many rows simultaneously. So we use global information to select the set of contiguous intervals that we then use as a test function. Finally, we have multiple we have multiple rounds of first sorting the rows, then fixing the row permutation, sorting the columns, and so on and so forth. And we do this for a super constant number of rounds, overcoming the one-shot barrier. Now I'll give some intuition for why contiguous intervals are a very natural family of test functions. So let's consider, so the key intuition is that locations where rows differ must concentrate. Let's consider the following very simple example. So we have two vectors u and v whose entries are in 0, 1, and let's say that their entries are sorted in increasing order. So this is like when the columns are already sorted. Now assume that ui is bigger than vi for all I, and that the differences ui minus vi are all either 0 or 1 over k. Now we have the following lemma, which is not hard to show, that says that for any subsequence I1 through IA of 1 through n, the total change of the difference ui minus vi over that subsequence is at most 1. So in this specific case, this implies that the set of locations where u and v differ can be partitioned into k contiguous intervals. If this is not the case, then we would be able to find a set of locations where the differences ui minus vi go from 0 to 1 over k back to 0 and alternate more than k times. And this would contradict the lemma. Now, why is this result interesting? So note that if there are less than k-squared locations where u and v differ, then their Frobenius squared error is less than 1. And this means that we do not actually need to separate u and v in order to achieve good overall Frobenius squared error when estimating the entire matrix. On the other hand, if there are k-squared or more locations where u and v are different, then what we've just shown implies that there are sort of k-contiguous blocks of average length at least k where u and v differ. Now, I'll briefly go over what our algorithm looks like, although there are many technical details that I will have to omit. So our algorithm is called multiscale sorting because it involves sorting at multiple scales. So first, let's say we look at all of the rows, R1 through Rn, to select a unit of contiguous intervals S that we will use as a test function. We split all of the rows into two halves based on their sum over S. Then we iterate over each of the halves. So for instance, for the top half, we use information from that half to come up with a new test function to split that half into 2 quarters. And we do the same for the bottom half. And then we iterate and split in halves at finer and finer scales. So again, in the first step, we're using information from the entire matrix. Then we're using information from each half, and then from each quarter, and so on. And then in the case when there are 2 unknown permutations, we alternately sort the rows, then fix the columns, fix the columns and sort the rows, then fix the rows and sort the columns. And we show that we can iteratively make progress at finer and finer scales. So to summarize, we have developed an algorithm for estimating bivariate isotonic matrices with unknown permutations. We obtain information theoretically optimal rates when there is 1 unknown permutation. And then we obtain improved rates when there are 2 unknown permutations. And sort of the key insights are we break several natural barriers that end in the negative 3/4, including the pairwise comparison barrier, the one-shot barrier, and also the barrier to algorithms that only look at sums of contiguous intervals. And that is all. So thanks.